He posted them on Twitter.
Okay, let's go ahead and get started. We're so lucky to be in the afternoon class because in the morning, the voltmeter didn't work, the battery was dead, everything went wrong. And I figured out what the problem was. We did not start with prayer. So, would someone be willing to pray for our demos today? Good with that.
I have a grandson who could pray up anything. We were visiting and he didn't want us to leave, so he just prayed for our flight to be canceled.
Our Father in heaven, we're so thankful for this wonderful day that thou hast given us. We're thankful for all of thy many blessings. Thankful that we could be here in Dr. Francis's physics class. We're thankful that we could all make it safely. And please help us to have the Spirit with us during this class so we can absorb the information that Dr. Francis teaches us. And please bless that all of the demos will function as they're supposed to, and that we can gain insight and information from those. And we're thankful for Dr. Francis and all that he does to help us learn. We're thankful above all for the gift of thy Son, Jesus Christ, and his atonement. And we love thee very much and say these things in the name of Jesus Christ. Amen.
Okay. We found last day that our current model sometimes left us with a pizza problem where it didn't give us a clear answer of which bulb should be brighter. And so today we're going to clear up all of those pizza problems. And we're going to do that with the idea of voltage. And we had more flow, more glow with the current model. More volt, more jolt, the best I could come up with. If you have something better than that, I'd like to hear it. Let's start with a review of our current model. The
Where's your baby?
The model was based on this assumption that more flow meant more glow. And that just seemed reasonable. If there's nothing flowing through the bulb, it's dark. If there's something flowing, it's lit. And it just makes sense that if some makes it glow, more would make it glow more. The next thing we discovered was that there was a relationship between the resistance, finish your sentence, of the circuit as a whole and the current, finish your sentence, through the battery. And the bigger the resistance of the circuit, the smaller the current through the battery. The voltage of the battery stayed 12 volts. That's printed on the side, but the current could be either a gusher or a trickle, depending on what we were hooking up to it. And then it was not what we added, but how we added it. We didn't care what it was, but whether we were adding it in series or in parallel. And whenever we added something in series, no matter what it was, we lowered the current through the battery. And every time we added something in parallel, regardless of what it was, we increased the current through the battery. Now, we also found that when Fred and his friends got to a junction and they saw a hard path and an easy path parallel to each other, more than half took the easy path. It favors the path of least resistance, doesn't choose unless we've got the special case of a short, and then they all go on the easy path, which is a perfect wire. The last thing that we learned, we didn't have any reasoning for. It just was an observation. And that is that any path that is parallel across the battery, in other words, has their own, if I hook this red bar up to the positive terminal of the battery and the black bar up to the negative terminal of the battery, if this branch of A, B, and C has their own connections to both sides of the battery, I can make any change I want in this branch. The other branch doesn't care. Likewise, I can make any change in that branch and this branch doesn't care. They're independent of each other. And today, before the end of this lecture, we're going to find out why that is. Now, the question is, when are things in series and when are they in parallel? When things are in series, everything that goes through one has to go through the other. There's no other path. If Fred goes through this one, he has to go through the other one. They have the same current, and by that I don't mean the same size current, I mean the same current. It's Fred and his friends going through one and then through the other. And if you're adding something in series, you have to break an existing line. You have to turn off the bulbs and shove the new stuff in. If you're doing it at the whiteboard, you have to pick up the eraser and erase part of the circuit, okay? When you add something in parallel, on the other hand, at the junction, Fred has to choose. Do I go this path to get back to the battery, or do I go that path back to the battery? But not both, one or the other. And when you find things in parallel, like B and C are in parallel, just the ordinary parallel, you find that they are connected by nothing but wire on both sides. Okay, B and C are connected by wire on this side, they're connected by wire on that side. And that's how you can recognize things that are in parallel. And you can add things in parallel without scissors or without your eraser, just by clipping them on.
We talked about that, like the pathway of A and the pathway of B are independent each other because they both have their own connection to the battery.
Yes.
But in terms of current, I don't know how they wouldn't affect each other, because if we have two blueberries from the battery, one of those blueberries is going to go to A and one of those blueberries is going to
No. Remember, the blueberries are going to favor the path of least resistance. And so if I make a change on A, that's going to change which branch is the path of least resistance. That's going to change the splitting. And we're going to find, if you'll just be patient, young Jedi, that we're going to find out why that can't affect the other branch. And it has to do with voltage. Okay. Now, I have an old exam problem. And so I need helpers. Where are my helpers? Thank you. Thank you. Over here we've got. Thank you. Appreciate you. Okay, coming in the back.
Bring that. Yes, it's a little. I don't know, biolab, just like that word, it's true, actually. I don't got physics or biolab, so. So Wednesdays, my friend, the word.
Get some of your. Thank you.
I think it's C and D.
Cute answer. Oh, I'm not supposed to pet him, right? I love dogs.
Like,
Do we have enough here?
Anytime you see nails.
Raise your hand if you don't have one, please. Everything I got. We need some more. Do we have any more? Thank you. Perfect.
right. It's like.
Thank you. Okay, how are we doing? Everyone's got one now? Okay. After class today, I will post a couple of sample exams with their solutions. There will be one problem on each of those exams that you won't be ready for until next Tuesday, but the other problems you'll be able to get started on. And you'll notice that on each of those exams, there's always a problem where you've got a circuit and the first thing you're asked to do is rank the bulbs 2 at a time. Now, when I was young and dumb, now I'm old and dumb, but when I was young and dumb, I used to ask my students, just rank all the bulbs, just brightest to dimmest. And when you've got 350 students and you're ranking all the bulbs together, there's just so many ways to get that wrong. And it took so long to grade that into the night with all the students. So I learned to just take 2 bulbs at a time. So in this circuit, which is brighter, A or C? Now, the first step in solving those types of problems is always to, first of all, this is the prime directive, figure out which branches are independent of which other branches, okay? And you can tell that because they have their own connections to both sides of the battery. So A and B are independent of the rest of them. Now, the next step after that is to draw those two branches the same. This would be A and B, of course. And the only way to get through, if this is branch 1 and this is branch 2, the only way to get through branch 2 with only 2 bulbs would be C and D. And if that were the circuit, boy, everyone would get a perfect score. They're all the same, Greg. They're all the same. But then you ask yourself, what's missing? Well, what's missing is this extra path with E and F. And so I would argue, I would say, oh, I told you that your most important tool in your box was being able to look and at 2 networks and say this one has more resistance. What I find that some people do is they try to make this really complicated categorization. Oh, well, this one has 2 bulbs in series in parallel with a bulb with the series with another bulb, and that one just has 2 bulbs. It's like trying to figure out which is better in poker, full house or 3 of a kind. I can't remember. Okay, you never do that. That's not going to be helpful. What you do is you say, branch 2 is the same as branch 1. Except. And then you say, what's different? Well, in this case, it'd be except the extra branch with E and F. And because that branch was added in parallel, but wait a minute, Greg, E and F are in series. Yes, they are a series network. I don't care. I don't care what they are. I care how they were added. And did I at any time pick up my eraser to put those up there? I did not. Okay, so they were added in parallel. And that means that when the current gets to that junction up there, it doesn't split 50-50, but some other way. More than half goes the easy way through C, and so C is going to be brighter than A. Are there questions on that? Now, if you turn that page over, that circuit, until late last night, was on your exam that you're going to be taking. And then I changed my mind and put a different circuit on the exam. Okay. but that gives you an idea of what is possible on the exam, the type of circuit that you would be asked to analyze. Okay, let's keep going on. What about C versus D? Which one's brighter, shouted out?
C.
C. Okay, C. And that's an all versus part argument. C is an indicator bulb for branch 2. Okay, everything that goes through branch 2 has to go through C, whereas D only gets part of that current. Now, if I wanted to write that mathematically, I would say the current through C is equal to the current through D plus the current through E. Okay, it's an all versus part argument. Now, if I were to compare E and F, that's easy. Which one's brighter? They're the same. And the justification is series. Series. Now, what about B and D? Tell your neighbor, which is brighter, B or D?
Yeah.
Pizza! I love my job. B is getting all of a small pizza. Where's the small pizza, Greg? Right up there. Okay. D is getting more than half of a large pizza. And there's a large pizza right up there. Okay. My current model won't tell me which of those is brighter. It fails. And so I need something else. I need something else. And before the end of this lecture, this is going to be trivial. We're going to be able to tell which is brighter, B or D. Okay, the current model fails. Now, in all of these problems, we start by ranking the bulbs, and then I will change the circuit. And remember, there's only 4 ways to change a circuit. We can add a new path, remove a path, clutter an existing path, or declutter a path. And in this case, what we're going to do is we're going to unscrew bulb F and leave the empty socket behind. Now, I find that a lot of people miss points on the exam because they don't really understand what that means. When you take a bulb out of the socket, that leaves a gaping hole behind. That socket is just, it's got a wire touching the bottom of the bulb and a wire touching the side of the bulb so that the current can go up through the filament and down the bottom. But when you take out the bulb, you've just got these wires that are separated from each other. Gaping hole, okay? And so the question is, if I take out that bulb F and leave the empty socket, first of all, what happens to A? Nothing. Nothing. And Brinley was just asking, how can that be? I removed a path. The current through the battery goes down. Shouldn't everything get dimmer? No. The prime directive, the very first and foremost thing that you keep in mind is that independent means independent. Okay, if I make a change in branch 2, branch 1 doesn't care. Well, how can that be, Greg? Well, let's say that with bulb F in there, let's say that I had 5 amps going down this way, and I had 7 amps going that way. That's going to give me 12 amps going through the battery. Now, if I take out bulb F, I've removed a path that's going to lower the current through the battery. But it can't change anything in this independent path. That's my first prime directive. And so that stays 5 amps. And now look, branch 2 now looks like branch 1. I've got 2 bulbs in series. And so this is going to change. I'll change colors. This is now going to go from 7 amps to 5 amps. And the current through the battery is now going to go to 10 amps. The current through the battery went down, but none of that decrease happened here. Because we changed this branch over here, we also changed the splitting ratio from more than half, less than half to 50-50. And those two changes were such that we didn't change the current through branch one. And we'll understand why in just a few moments. Be patient. What happens to bulb E? Dark, out. Is it shorted out? No or heck no? Heck no, it's on an incomplete path. An incomplete path is going to lower the current through the battery. A short is going to increase the current through the battery. Those are different. What about bulb C? Bulb C is an indicator bulb for its branch, branch 2. We've removed a path. That means the current through the battery goes down. The decrease can't happen in branch 1, so it has to happen in branch 2. Everything that goes through branch 2 goes through C, so C gets dimmer. Check that your neighbor would have gotten this exam question right. DNA are exactly the same as each other. What we really care about is the whole branch. And this whole branch is easier to get through than this whole branch. Because they're exactly the same, except for this extra path. And whenever I add something new, I make it
That's
easier.
kind of like all the stuff, like, I had to.
Yes, C is gonna be brighter than either of these. Because of that extra path.
No, like.
Okay, I've got another exam question. I need my helpers again. Helpers, where's my helpers? There we go.
Like, why? Just.
Okay, hand them out like fish and manna. Thank you, Elizabeth.
He's fine. If you connect both of that. So it's just like series. I'm gonna do the same.
Just pass them forward.
I saved it, but I told him to see her.
These extras.
I think you run and you're just getting. You have your. Yeah. I think. Why are B and C not the same? Just the. It's like I used to upgrade. Maybe it is. Okay, I understand.
I'm not very big.
See. In the head.
He's not very good.
Okay, raise your hand if you still need one, please. Thanks. Okay. Yeah. Oh, how many do you need? Just one.
No, bro.
Think about that.
The harder one, yeah. Learned it yet. That's what we're learning today.
Okay,
But.
again, we start by ranking the bulbs, and then we're gonna make a change to the circuit. First, we're gonna compare A and B, which is brighter. A, it's an all versus part. A is an indicator for the circuit, and so it's the brightest. If I compare B versus C, again, it's all about figuring out which side, left or right, is harder to get through. So what I would do is I would draw both of those the same, and then ask what's missing. So I would put bulb A and then B, and then D, and then C, and then E. And if this were the circuit, it would split 50-50 at that junction. But when I ask what's missing is bulb F. And I did not at any time pick up my eraser. And so that means that the current is not going to split 50-50, but more than half is going to go the easy path, less than half is going to go the hard path. And so that means that C is going to be brighter than B. If I compare B versus D, that's series, they're equal. But when I compare D versus E, I get a problem. I get pizza. D is getting all of this little pizza. And E is getting exactly half of that big pizza. And so I can't answer that with my current model. Before the end of this lecture, that's going to be trivial. That's going to be trivial. Now, if we turn the page over, we change the circuit by adding a connecting wire, a perfect wire, from point 1 to point 2. Roman numeral 1 to Roman numeral 2. Now, I've got some questions for you with your clicker. If you get your clicker out. The first question, does bulb C go out? Yes, no, or I don't know. Let me get this started. Okay, now you can click.
No, it should. Is it? Oh. I think E definitely goes out. It goes through somebody. Yeah. Unless it would all go higher because.
Okay, last call. Get your vote in. Get your point. Okay, 5 of us do not know, but the results suggest that there's more than 5 that don't know. Okay, so that's okay. We'll figure it out. Next question. Does B go out? Yes, no, or I don't know. With your clicker, please. Does B go out?
Yes, B should go out.
Yes, they were left last day. So one of them, vote on both of them.
Totally see your mind.
On both of them, and then you're sure.
Like the current slowly like.
So it's gonna split, like something's gonna go.
Okay, last call. Okay, again, 6 people don't know, and 1 people chose D. Let's talk about that. Here's a tool for your toolbox. It turns out, for a reason that we will learn in just a few moments, a connection on a wire can be moved without changing the circuit at all, without changing the brightness of any of the bulbs. I can move this connection anywhere along a wire as long as I don't cross an element like a bulb or a switch or a battery or a resistor. That means I can move that connector right there. I can move it to there, doesn't change a thing. I can move it to there, doesn't change a thing. I can move it to there, doesn't change a thing. And now you can see clearly B is shorted. Nothing will go through B. It's dark out. But C is not shorted. the brightness of C is going to change, but it's not going to go out, not going to go out. So now we're asked, how do these different bulbs change when I put that wire from 1 to 2? Well, bulb A is the indicator bulb. All the current through the battery goes through A, and we just added a path to my circuit. And that means A gets brighter. The current through the battery goes up. Well, B, we just said is shorted out. It's dark. If I look at bulb D, there are two changes going on. D used to be on the hard path, getting less than half of the current through the battery. Now it's on the easy path, getting more than half of the current through the battery. D's share of the total current went up. Oh, and the total current through the battery also went up. They're both trying to make D brighter. D is going to get brighter. But when I look at bulb C, now we got a problem. Its share of the total current went from more than half to less than half. Its share of the total current went down. But the total current we're sharing went up. One of those changes is trying to make bulb C dimmer, and one of them is trying to make it brighter. And our model is not telling us which is going to win out. So that's a failure of the model. C is now getting a smaller share of a larger total current. Yes, sir.
Why are these two branches not independent? I guess I'm just not understanding the independence, when it applies, when it doesn't.
I'm sorry?
These two branches here, why are they not independent?
Oh, because of bulb A. You're only independent if your branch has direct connections with nothing but wire to the positive terminal of the battery and the negative terminal of the battery. Otherwise, they're just vanilla parallel, the ordinary parallel that's not independent. Okay? Now, we keep running into these pizza problems where our model fails. So let's try something else. And the something else is going to be voltage. And let me just remind you what we learned about voltage earlier. And that is, if I put a voltmeter across that battery, when I say voltage, what I really mean is voltage difference from some point A to some point B. In this case, from the negative terminal of the battery to the positive terminal of the battery. And if it's a 12-volt battery, I get a reading of 12 volts, which I interpret as 12 joules for each coulomb. And that's how I visualize what's going on. Every coulomb that goes through that battery from the negative terminal to the positive terminal, it's handed 12 joules of energy chemically through a process we can't possibly understand in this building, okay? Now, if I measure the voltage difference across that bulb, I also get 12 volts, but now it's a 12-volt drop. And I interpret that as the coulomb giving up the 12 joules. Doesn't lose the 12 joules per se. It transforms it into heat, and then that heat causes the bulb to light. It goes into other forms. Now, this is the cartoon that's running in our head, where the dark red balls are the coulombs that are at the high electric potential energy, and the pink ones are the ones at the bottom of the cliff at the low electric potential energy. And we just see those dump trucks go around and get more energy and take it to the bulb. Okay? Now, what about the currents? Well, those are the dump trucks, not the energy, the dump trucks. And what goes around comes around. Whatever's going through that bulb is also going through that battery. Now, if I've got two bulbs in series, we can show that those are dimmer. So if I have two bulbs in series, I get two dim bulbs, but they're equally dim. And what that tells me is that I've got the same current through them. Again, not just the same size, but the same Fred and his friends, first going through the top one and then going through the bottom one. Now, that current just keeps on going around and through the battery. And if I measure the voltage across the battery, I still get 12 volts or 12 joules for each coulomb. But if I measure it across the bulbs, what I get is 6 volts and 6 volts. And let me just show you that real quick. If I do it from one side of the 5.7, almost 6. Okay, if I do that down here, 5.7. My battery's not giving me 12. I should have paid more. Okay. Now, the cartoon that we have in our head, well, first of all, what do we mean by sharing? With the current going through the bulbs, we're sharing like a book or like a pie? Book. Okay. What about the voltage? Is that being shared like a book or like a pie? Pie. Now you get to say pie. Good. Oh, and Saturday is what day? Pie day. Eat some pie. Okay. Now, this is the cartoon running in my head. The darker the ball, the higher the electrostatic potential energy. So those dark red ones are at the top of the cliff. The ones in the middle that are kind of medium red, those are halfway down the cliff, and the pink ones are at the bottom of the cliff. And they just go around. The coulombs give up half their energy in the first bulb, half their energy in the second bulb, go back to get more energy. Okay? Now, we have been making this comparison between electrostatic potential energy and gravitational potential energy. Let's formalize that with a field trip. What you're seeing here is the Gallatin Valley in Montana. Montana State University is right there. This is their poor excuse for the Y. That's just a little tiny M. Weak sauce, okay? But what we're going to do is we're going to start here on campus, and a plane is going to magically transport us to the top of that peak. And in the process, hand to us, in a process that's very complicated, gravitational potential energy. And if we look at the formula for gravitational potential energy, the average mass of a person is 75 kilograms. G is 9.8. We're going to call it 10 newtons for each kilogram. And that's 1,000 meters high. Okay. So on average, each person has been handed magically 750,000 joules of gravitational potential energy. Now, we want to get back to campus. And the easiest way to do that is go along the ridge and then down to the M and then back down to Ralph Street and back to campus. Now, what's going to be the change in gravitational potential energy if we go down that path? Yeah, what goes up must come down. And so the change in gravitational potential energy is going to be negative 750,000 joules per person on average. Okay. And because that's actually every year they had what's called the Ridge Run that was run along this ridge. I lived in Bozeman for 31 years. Guess how many times I ran that?
0.
You got it. 0. Yeah. He knows me. But I do eat pie on Pie Day. Now, because that's the easy path, all of us are going to take that path almost, but not Brinley. No, she sees another way. She sees a way right down the front of that cliff and back to campus there. Okay. Now, what's going to be the change in gravitational potential energy on that path? The same. Negative 750,000 joules per person on average. Okay. And that's independent of which path we take back to campus. Now, because this is the easy path, we get a large current going that way. A lot of us go that way. Because this is a hard path, a high resistance path, we get a very small current, just Brinley, going that way. But all of us Everyone in this group and Brinley all went up on the plane. Okay? Now, do you see the electric circuit there? When you look at that picture, do you see the circuit? How? There's the circuit. Where's the plane? The plane. Where's the plane? The battery. Instead of handing each of us gravitational potential energy, it hands each Coulomb electric potential energy, brings them to the top of the cliff, the top of the peak. And then, when I look at the brightness of the bulbs, I realize that this is the easy path that all of us went down. And this is the hard path that only Brinley went down. But if I measure the voltage across the battery, I get 12 volts. If I measure the voltage across this bright bulb, I get 12 volts. If I measure the voltage across this dim bulb, I get 6 volts. Okay, and this one would be 6 volts. No matter which path I take from one side of the battery to the other, I've got to have a drop in voltage of 12 volts if it's a 12-volt battery. Now, there's another thing here that's very important, and that is the brighter bulb has more volts across it. Now, we used to say more flow, more glow. If I saw one bulb that was really bright and one that was really dim, I could say there's more current flowing through that bright bulb. But now I've got another tool in my toolbox. If I see a bright bulb and a dim bulb, I can say there's more volts across that bright bulb. And those are not unrelated. The voltage is voltage difference from one side of the bulb to the other. Think of it as a pressure difference from one side to the other. And the bigger that pressure difference, the more current is going to be pushed through that bulb. The bigger the push, the voltage, the bigger the flow, the current. Now, folks, I beg you, I plead with you to be careful with your words so you don't mix yourself up when you take that exam. Whenever you're talking about current, it goes through the bulb. It goes through the wires. It goes through the battery. But don't ever say the word volts and through in the same sentence. That's just sick and wrong. The volts don't go anywhere. They're a voltage difference from this point to that point, like the elevation difference from the top of the peak to the bottom of the peak. Okay? We always say the volts are across the bulb. The volts are across the battery. The volts are across the resistor. But the current is what goes through. Check that your neighbor knows the difference between voltage and current.
Sharing. Space.
That was only true when we had a uniform E field.
Any given path.
Nothing.
Next week, Brian.
The one that.
Okay.
That goes from.
Oh, yeah.
Now, if we look at the current, I've got a bunch of current going through that bright bulb, not so much current going through the dim bulbs. But everything has to go through the battery. Okay, this is all of us on the ridge. This is Brinley, but we all went up in the airplane. Okay, so this is the sum of those two that are in parallel. Okay, now here's the voltage model, and it's so simple compared to the current model. Voltage is nothing more or less than the energy that's delivered to each Coulomb in the battery and used up in the bulb or a resistor, okay? And what we find is that if we have more voltage across the bulb, it's brighter. And that's why we say more volt, more jolt. More flow, more glow, more volt, more jolt. But here's the real essence of the voltage model. What goes up must come down, just like with gravity. And that means that the voltage rise across the battery has to equal the voltage drop around any loop from one side of the battery to the other, any loop from one side of the battery to the other. That's it in a nutshell. That's all. Now, let's see if you understand that all. We've seen this simple circuit before. We know what it does. We know that that bulb on top is an indicator bulb, and it gets all the current through the battery. These guys each share the current evenly, 50-50. And so if I look at the brightness, this bulb would be the brightest and these two would be the dimmest. Everyone comfortable with that? Now, if I were to ask you, what can you tell me about the voltage across bulb A? Is it greater than 6 volts, equal to 6 volts, or less than 6 volts? With your clicker, please.
Be 12 and then be 6, right? Parallel, they don't. Because now this one, when I was doing the homework last night, if you're saying it's the bottom one, though, it is being sort of drops. Which is right at the same time. How we're gonna go deep and then drop. It's got that.
Okay, last call.
Next to it. That's fine.
Okay, we're all over the map.
Oh, I see.
The reason we're all over the map is that currently in the room, we have two separate models that we're using. Okay? Some of us, if we call that VB and VC, some of us are using this model on the left, where the voltage of A and voltage of B and voltage of C add up to 12 volts. Some of us are using this voltage on the model on the right. The voltage of A plus the voltage of B is equal to 12 volts. Find out from your neighbor which one they're using. Which model are they using right now? Okay.
It's different with me. That's what I meant. Yeah.
The key to understanding this is to follow Fred. Fred has to go through bulb A to get back to the battery, okay? But then Fred has a choice. He can either go through B or he can go through C, but not both. And any path that Fred takes from one side of the battery to the other has to add up to a 12-volt drop. And so the correct model is the one on the right, not the one on the left. Now, let's keep using that. I know that this voltage plus that voltage adds up to 12. I also know that this bulb is brighter than that bulb, and a brighter bulb has more volts. That means that A has to have more than 6 volts, and B has to have less than 6 volts. I'm going to make up a number. If the voltage across A is 9 volts, this has to be 3 volts, and this has to be 3 volts. Because any path, either A plus B or A plus C, has to add up to 12. Now, a consequence of that is that any parallel paths, regardless of what's on them, regardless, have to have the same volts across them. That just makes sense, because if you start from the same place on the mountain and you come down to the parking lot, it doesn't matter which path you take, you're taking the same change in elevation either way. Either way. Check on your neighbor. Do a buddy check.
Have the same. Yeah, that's good.
Okay.
Going on that path. Brightness. You have to go.
I have a question for you. Is bulb A in series with bulb B? No or heck no? Yeah. Series means everything through A has to go through B. But everything through A doesn't have to go through B. So what is in series with A? Well, what's in series with A is the network of B and C together. Now, one way to use the voltage model is to put things in boxes that are in series with each other. Because things that are in series with each other, the battery has to shove the same number of coulombs through each box every second. Otherwise, they get piled up somewhere, right? And so if I want to know which of those boxes has the most volts across it, I look at which box is harder to get through. Because I can think of the voltage as the of the battery. That's a technical term. Okay. The battery has 12 volts of and it's got to shove coulombs through both of those boxes. Well, what I find is that if I measure the voltage across that upper box, I get a bigger voltage across the upper box. And I also can see from what I know about equivalent resistance that that's got the bigger resistance. Okay. And that's how you can use the voltage model. For series networks, and this only works for series networks. That's a big caveat. Only for series networks, the voltage drop is greater across the larger R. Across the larger R. Because that's where the battery has to do the most oomph to get the coulombs through. That makes sense? Well, let's go back and solve some pizza problems, shall we? Let's put this this new model to work. If I want to compare B and D, remember that didn't work out for the current model. But if I use voltage and I say that's a 12-volt battery, I look down this first path and those bulbs are in series. They're equally bright, so they have the same amount of voltage across them, and it's got to add up to 12. Well, that's 6 and 6. Easy peasy, okay? I know from the current model that this bulb is brighter than A or B. If these guys have 6 volts, C must have more than 6 volts. Now, I also know with the voltage model that the voltage across C and the voltage across D add up to 12. So if this is bigger than 6, let's say 9, this has to be smaller than 6, let's say 3, okay? And now I can compare, I can compare B versus D. Okay, if this is 6 and this is less than 6, B is going to be brighter than D. Questions on that? Whenever you get stuck with a pizza problem, switch over to voltage, okay? And that will fix your problem. That will fix your problem. Now, you'll notice that in this, what I just did, I had to invoke the current model to argue that C was brighter than A. So I was really using both models together. But I could have solved this just with voltage. And I do that by putting boxes around things that are in series. And in branch 1, A is in series with B, and they're equal resistance. And so if I look down this first branch, I divide up the 12 volts, the oomph, evenly, 6 and 6. But if I look down this second branch and put things in boxes that are in series, well, this box is exactly the same as that box, except for this extra path with E and F. That's going to lower the resistance of this box relative to that box. And that means when I divide up the oomph, I'm going to put more than half up here, less than half down there. And now when I compare B and D, B is getting half of the battery voltage, D is getting less than half of the battery voltage. So that's a full-on voltage model. Okay? Check that your neighbor followed that. Do a buddy check again.
I'm the greatest.
I think I the same, but they just each other. So people with 6 volts, he's brighter, so it's kind of pretty 6 volt. Be the same. He's the 12. It's 2.5.
Yes, sir.
That's out of the the even if you go from the top of the
Yes, yes, yes. Good. Beautiful. Okay. This gentleman just said something profound, and that is if C has 9 volts across it, D has to have 3 volts across it. But any path has to add up to 12. And so these guys have to have 1.5 and 1.5, so that I've got 9, 1.5, 1.5, that's 12. Any path's got to add up to 12. Good. Good. Yes.
What happens if we unscrew them?
If we unscrew F, then this stays 6 volts, that stays 6 volts. This now has the same resistance as this box because we remove that path. And so this becomes 6 volts and this becomes 6 volts. And so C will get dimmer and D will get brighter. Okay, see how powerful that is? And this also explains why those parallel branches across the battery are independent of each other. Because if I hook this positive terminal of the battery to that red bar, and I take the negative terminal of the battery and I hook it to that black bar, any branch that is connected to the red bar and the black bar directly has 12 volts across it. Come heck or high water, I can change this circuit. This guy still has 12 volts across it, a pressure difference of 12 volts. I can change this circuit, and this one still has 12 volts across it. It doesn't care. That's why they're independent of each other, is because the voltage stays the same if they're connected to both sides of the battery. These guys are parallel, B and C, but not across the battery. And so when I unscrew this bulb, that changes the voltage here, and that's going to change the voltage down here. It's no longer fixed at 12 volts. So these guys being parallel, not good enough. Got to be parallel across the battery to be independent. Okay. Now, last day, we talked about putting that indicator bulb there. And we found that if we did that, D got brighter. But we couldn't say what happened to A. It was a pizza problem. We got stuck. So let's do that now with voltage. If I close that switch, what do I do to the current through the battery? It goes up. I've added a path, made it easier for flow. Now, that means that the current through this indicator bulb goes up. More flow, more glow, it gets brighter. But also more volt, more jolt. If it got brighter, that means the volts across it got bigger. Now again, any path from one side of the battery to the other has to add up to the 12 volts of the battery. If the voltage across this bulb got bigger, the voltage across A gets smaller.
But V equals IR.
V equals R, yes.
Yeah.
Say it right.
Anyway, so, but here's the thing. So we talked about like resistance goes down for the circuit, which current goes like increases through the battery, but like, so why would we talk the same there? Because one goes less and one goes higher.
Okay, when you use V equals IR, you can use it globally or locally. When you use it globally, the V in V equals IR is V of the battery. The I in V equals IR is the current through the battery. And the R is the equivalent resistance of the circuit as a whole. The whole circuit. And if I use it locally, the voltage across bulb A is equal to the current through bulb A times the resistance of bulb A. Okay? So this is what we were using, the global. Okay? Now, bulb A gets dimmer. So let's go back to this problem here that we were working. The first pizza problem on the front of the page was comparing bulb D to bulb E. And I'll remind you, D got all of the small pizza and E got half of the large pizza. Now, whenever you're comparing two bulbs with the voltage model, you want to pick a path that goes through each bulb, through bulb D and through bulb E, and those paths have to start at the same place and end at the same place. Because they're starting and ending at the same place, they have to have the same voltage drop across the red path as the blue path. It's like starting at the same place on the mountain and coming down to the same parking lot. You got to come down the same number of meters each way. Now that means that if I add up the voltages on the red path, B plus D, it's got to equal the voltages across the blue path, C plus E. Now remember, we're trying to compare D to E. And the first thing we got to do is compare the other two. Okay? If I compare the other two, and I've already done that, I know that this was the easy path through C, and so C is going to be brighter than B. We did that with our current model, right? Well, if the blue team wins this round, and it turns out to be a tie overall, the red team has to win the other round. Okay, and so that means bulb D is going to be brighter than bulb E. Now, if me and my brother fight you and your sister and it's a tie, and if my brother beats your sister, what does it say about you and me? Maybe that's not a good example. That's more violent. What I've got here is a red team.
Does that assume that they're all ohmic, that the resistance doesn't change when more current goes through it?
What did he say? Say it again, louder.
Does that assume that the bulbs are all ohmic, that the resistance doesn't change?
No.
The
No, it does not. And that's the beauty of this, is that it does not require the bulbs to be ohmic. It works either or. Okay. It'll also work with things that are ohmic, like resistors that we work with. But it's just this is we call it Kirchhoff's loop theorem. And Kirchhoff gave us two grand theorems. The loop theorem is that any path from one side of the battery to the other has to have a drop equal to the battery rise. And his other theorem is the junction theorem. Whatever goes into a junction has to come out. You know, if I've got 2 amps going down the left and 3 amps going down the right, I've got to bring in 5 amps to. Now I've got a red team and a blue team, and I gave each of those teams $1,000. Okay. And they divided up the $1,000 any way they wanted to. And I'm doing it on these whiteboards because I didn't really have $2,000. Okay. But each team is going to split up the money, shove it into their pockets, and write down on the whiteboard how much money they got in their pocket. And then we're going to bring up a member from each team. And this person has $406 when they empty their pockets. And this one has $136. Red team wins. Okay. Now we bring up the next contestants. Do I need to uncover these? No, you know that if the red team won the last one, each team started with $1,000. The blue team's got to win this time, right? Whichever won the last one isn't going to win this one because it's a zero-sum game. $1,000 each. Does that make it more real when we talk about money? Okay. Okay, my son worked for Goldman Sachs for a while, and his job was to bring to the CEO and the vice presidents the net worth of the company every week. And he had to bring it to them to the nearest $100 million. So how would you like it if on the exam you just had to get to within the nearest 100 million? Okay, that's not going to be on the exam. The other way to use the voltage model is when you're just comparing a bulb to itself. You're not comparing it to another bulb, you're comparing it to itself before the change and after the change. When I put that connecting wire across bulb B, what happens to bulb C? Well, when you're using the voltage model for that, you need to take a path that goes from one side of the battery to the other side of the battery that goes through bulb C. And that's got to add up to the 12 volts of the battery. That's Kirchhoff's loop there. Now, if you want to know what's going to happen to bulb C, look at what happens to the other bulbs. Well, by adding that path, shorting out B, the current through the battery goes up, so A gets brighter. Its voltage increases. And that means C and E have to decrease. I know they're going to go the same direction because E always gets exactly half of the current that C had. And so if C gets dimmer, so does E. And so to keep this equal to 12, if this one gets bigger, those have to get smaller. That makes sense? And so the voltage model immediately answers our question. Okay, let me summarize here. With the voltage model, we put things in boxes that are in series. And the voltage for the series elements divides, like for a pi, and it divides evenly for equal R's, but otherwise the voltage drop is greater across the greater or lesser R? The greater R. The greater R. Okay. So if I can just kind of summarize it, if we've got a parallel branch network, then the current is going to split at that junction, but the voltage across the two is going to be the same, regardless of whether the paths are the same. I showed them similar or the same, but that doesn't have to be the case. I could have had 27 bulbs on the right side. If I've got a series network, we have the current is the same because there's no other path, but the voltage divides. The bigger the resistance, the bigger the voltage share. Now, a letter from the class. Greg, I'm in your 206 class. That's what we used to call 106. Everything's inflated in Montana. And I used to have a grasp of what would make a bulb brighter. After I learned the voltage model, I'm completely lost. Anyone feel that way? Current will take the path of least resistance, so the bulb that sees more current will be brighter. I understand this to mean less resistance, more glow. In the voltage model, there will be a higher voltage drop across the bulb with more resistance. I understand this to mean more resistance, more glow. To my brain, this seems to be a contradiction. I know the errors in the way I'm thinking about this, but I can't seem to find it. Would you please help me? Now, this was very mature to recognize that there must be some kind of mistake in their reasoning. Let me see if I can help out. So what he's saying is that if I've got, two things and one has a big resistance and one has a small resistance, the current is going to split with more than half going that way and less than half going that way. Whereas if I have two things that are in series, and I've got a big resistance here and a little resistance here, this is going to get the bigger voltage and this will get the smaller voltage. And then he says, if I have a bulb in here and a bulb in here, this bulb with the smaller resistance is going to be brighter. Whereas if I have a bulb in here and a bulb in here, the bulb with the bigger resistance is going to be brighter. You see where the flaw is? If each of these boxes contains one bulb, they're identical bulbs, okay? I can't have this bulb have more resistance than that bulb. And so what we're going to do is we got to have something else in here, like this is two bulbs, okay? And that means this would be two bulbs. And so now the conundrum goes away. This is the harder path. And so I'm going to get less flow and these guys will be dim and that one will be bright. This one will have a big voltage across it. This will have, each would have half the voltage across it. Likewise, if this is a 12-volt battery, this box is going to have 8 volts across it, and this would have 4 volts across it. But each of these bulbs would just have 4 volts across it. The flaw is saying, there will be a higher voltage drop over the bulb with more resistance, okay? Now, you can go down to Lowe's and you can buy bulbs that have more resistance. A 40 watt bulb has more resistance than a 100 watt bulb. And if you hook those up the way they're supposed to be hooked up in parallel, the 100 watt bulb is going to be brighter because it gets more current through it. But if you hook them up the way they're not supposed to be hooked up in series, the 40 watt bulb will be brighter than the 100 watt bulb. So what I'm saying is physics works. Okay, chemistry doesn't. Go somewhere else, people.
Like in theory, maybe.